Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, professor in University of Delhi. Today, we are going to discuss about another module which is going to be on introduction of secondary ion mass spectrometry, which is briefly used or called as SIMS. This is a part of the surface analytical technique, and it comes from the second part of this unit. What is secondary ion mass spectroscopy? How this secondary ion mass spectroscopy can be used, or how it came into being? What is the underlying principle of this technique? Answer to all these questions would be answered in the upcoming set of slides. So here we go. To begin with, I would like to give you the brief about this module. Initially, we will be studying about the basics of SIMS, which is, of course, as I said, is abbreviated as SIMS. What exactly is this? Then we will proceed to the background of the history of secondary ion mass spectroscopy, which includes the year of invention or discovery, along with the name of the scientist who did this. And from here, we will be going through the phenomenon of secondary ion mass spectroscopy. That is about the principle behind this technique called SIMS. Moving from here to the next would be about the classification of SIMS, the SIMS equation, and the term of practical SIMS. Then we shall come to the study about the static and dynamic SIMS, bulk contamination, composition studies, and the SIMS equation would also be ultimately studied in this. What is SIMS? It is a technique that is used to analyze the surface of solids. As we will all know, that the knowledge of chemical composition is a very important parameter in the study of materials. Therefore, it is basically used to examine the contribution of the solid surfaces and the thin films. It involves the use of highly energetic beam to sputter the material from the surface of the sample and then analyzing that ejected ion. The high energetic beam that is being used to sputter the material is termed as primary beam, and once primary beam are ejected into the material they interact with, that is the sample, causing the ejection of the ions, and the ions that are ejected out from this surface are termed as secondary ions. It is the secondary ions which are analyzed by the analyzer for the chemical composition of the sample surface. The amount of ionized material that is being sputtered depends on the various factors such as chemical structure of the substrate, the ionization efficiency of the substrate, ionization efficiency of the element that are present within the sample surface. The foremost important parameter in this study shall be the nature and the energy of the primary ions to be used, which talks about what is SIMS. As I had said earlier, SIMS stands for secondary ion mass spectroscopy. Here in this spectroscopy, the mass to charge ratios of the above ejected secondary ions are used to determine the elemental, isotopics, and molecular level composition of the surface to a depth of about 1 to 2 nanometers, and is measured with the help of a device termed as mass spectrometer. Based on the mechanism of beam in, beam out, this is the principle which is used in this spectroscopy. It is the most sensitive analytical technique whose detection limits ranges from parts per million to parts per billion. That will indicate how sensitive this spectroscopic technique. Again, it continues to explain about what is SIMS. The secondary ion mass spectroscopic technique provides a unique combination of extremely high sensitivity for all elements from hydrogen to uranium. That means it can work for a very light element like hydrogen to a very heavy element like uranium with equal ease. Then it has high lateral resolution, which again continues with the same phenomenon. Here it talks about low background that allows high dynamic range. This technique is destructive by its nature. It can be applied to any type of material, which will include insulators, semiconductors, or metals for that matter, that can stay under vacuum. Here it talks about the history of secondary ion mass spectroscopy. This was originally started by Sir J.J. Thomson, and he did this in 1910. He noticed a release of positive ions and neutral atoms coming from a solid surface that were induced by ion bombardment. Then the references of Sir J.J. Thomson have also been shown. Hertz and Wiebach in 1949, with the help of improved vacuum pump technology, made it possible about the first prototype equipment of SIMS. After a few years, around 1950, the first complete SIMS equipment was designed by another set of scientists whose names are Hong, Brodley, Beskay, and Werner. With the passage of time, rapid development took place both in the analytical application as well as in the instrumentational development towards this. Argon was the main primary beam which was used in this particular instrument. Then in 1960s, or we can call it early 60s, another group independently developed this instrument, which we have been calling it as SIMS. One group was led by Liebel and Herzberg, and the other group was by Casting. These instruments were used to examine the composition of the surface material and thin film by altering the surface specimen with the focused primary ion beam and collecting the ejected secondary ions.
Principle of secondary ion mass spectrometer. The interaction of primary ion beam with the sample, of course under vacuum, provides sufficient energy to ionize many elements. If the primary beam is composed of positively charged ions, the resultant ionization favors production of negative ions. Primary beams of negative ions favor generation of positive ions. Although most atoms and molecules removed from the sample by the interaction of primary beam and the sample surface, referred to as the sputtering, are neutral, a percentage of these are ionized. These ions are then accelerated, focused, and analyzed by a mass spectrometer. In dynamic SIMS mode, the primary ion beam exceeds the static limit, producing a high yield of secondary ions. This technique is used for bulk analysis of elements and isotopes, and is particularly well suited for analysis of isotopes and trace elements in minerals. Alternatively, static SIMS uses a much lower energy primary ion beam. This technique is typically used for analysis of atomic monolayers on material surface to obtain information about molecular species on the material surfaces.
The phenomenon of SIMS continues and is shown very clearly in the photograph here. In this slide, which deals with the basic principles, or we can say the phenomenon of SIMS, it is very much clear from the flow chart that the underlying phenomenon of SIMS is used for a proper analysis of the material on the surface. We have discussed before also that SIMS is a sputtering phenomenon. When high energy beam is shown, as shown in the figure, that is also commonly known as primary beam. When it collides with the surface of solid, energy is being transferred from the primary particle to the atom of the material or sample that has to be analyzed. Some of the primary ions here can be scattered back, but most of them transfer their kinetic energy to the lattice through the process of collision and are enforced into targets according to their energy, mass, and impact angle. The final result is not only the emission of secondary ions, but also the emission of low energy electrons that may be in the form of O-share electrons or photons from a visible to X-ray, depending upon the primary energy, depending upon how strong the energy was. Neutral particles and excited clusters also come in. These secondary ions that are being emitted out are further passed on to the analyzer that can further analyze this data which is being displayed on the computer screen. Phenomenon of SIMS. What is the main phenomena on which SIMS is based? When energetic ions, atoms or molecules integrates upon a solid, this phenomena leads to the ejection of particles out of the target from near approximately 1 nanometer, the point of impact. This form of wearing down goes under the name of sputtering. As the liberated species stem from very shallow depth, these carry information about the local instantaneous composition of the target surface. The same principle of SIMS. By continuing bombardment with primary species for a prolonged time on increasingly deeper sputter crater that develops while studying this. As a result, the sputtered secondary species will then reflect the composition inside the target. By dynamically registering the number of ejections per unit time, after these have been preferably uniquely identified as a function of time, one thus obtains, perhaps a distorted one, depth distribution of these species. As I've been saying, that this is a very important technique, phenomenon of SIMS, which we have been briefly terming it. This technique is known as sputter depth profiling. In the case of SIMS, the sputtering by primary ions serves two purposes. In order to generate emission from the target surface for in-flight analysis and to peel the surface off. In another variation, sputtering is exclusively used to expose the inner part of the sample for analysis by some of on-target surface sensitive analytical techniques like O-share electron spectroscopy. It is briefly put it as AES, or the pronunciation is O-share electron spectroscopy. To move further in this direction, students, you will realize the secondary species that are generated are charged. Obviously, the secondary ions being charged have the advantage that the standard, well-established and reliable spectrometer methods can be applied to discriminate on mass for, or rather we can call it mass over charge ratio. In general, a perfect mass separation is possible only when a unique identification for all the ejected elements and atomic ion is possible, which we are doing in this case. What are the particles or what are the forms of practical SIMS are given? What forms this technique can take have been described in this particular slide. There are three DOMs of practical SIMS. One is static SIMS, the second one is dynamic SIMS, and third, bulk contamination composition studies. Static SIMS are explained here. In static SIMS, the presence of molecules or the adsorbates at the surface is the subjected one to analysis. Primary characteristics for SIMS is very low primary beam density. In order to avoid excessive damage or distortion of the surface or surface impurity population, a large analyzed area is required. Now moving on to the dynamic SIMS. As I said, there are two kinds, and this is the second kind. In dynamic SIMS, the depth distribution of impurity range is important. Characteristic feature for DSIMS, that is dynamic SIMS, is it is very intense primary beam that is usually well focused to allow the focusing over a very small area. In order to get a reasonable erosion rate, combined with a flat sputter crater in the bottom of which only a central part actually contributes to the analysis to avoid redeposition of the crater walls. Well, if I continue further in this, the type and energy of the species that are impinging on now on the are of primary importance. During depth profiling, previously implanted primaries will be encountered and may influence the secondary ions. Detection limits obviously are going to be very important that are attainable, and depth resolution, they all depend upon the sputter yield and the damage or the disturbances to the original profile indicated by the bombardment erosion. So the primary beam parameters must be optimized in accordance with the analytical requirement to the particular sample at hand.
In static SIMS or SSIMS, the aim is to obtain sufficient signal to provide a compositional analysis of the surface without actually removing a significant fraction of a monolayer. This requires the use of very low ion fluxes, which is around 10 to the power 12 centimeter square, centimeter minus 2, that is 10 to the power 12 per centimeter square, to ensure that each ion is statistically likely to impact upon fresh undamaged surface and that the sputtered secondary ions are representatives of original surface rather than the surface that has already been damaged by earlier ion impacts. In this form, the technique is capable of providing information about adsorbed molecular layers or the topmost atomic layer of the solid surface. The example is static SIMS spectra from the surface of PTFE, that is polytetrafluoroethylene. In this spectra, note that the substantial difference between the positive and negative ion spectra. In each case, the most intense peaks corresponds to relatively stable positive and negative ions respectively. While static SIMS concentrates on the first top monolayer, providing mostly molecular characterization in dynamic SIMS mode, bulk composition and in depth distribution of trace elements are investigated with a depth resolution ranging from sub-nanometer to tens of nanometer. Dynamic SIMS instruments are equipped with oxygen and cesium primary ion beams in order to enhance respectively positive and negative secondary ion intensities. Starting from the surface or going through the interface, while the primary ion dose implanted in the target increases, the primary species concentration, oxygen or cesium, will reach an equilibrium depending on the sputtering conditions and the nature of the target. This equilibrium corresponds to a sputtering steady state, and as soon as it reached, reliable quantification is possible with reference standard samples using relative sensitivity factors. One of the main applications of dynamic SIMS is the in-depth distribution analysis of trace elements, for example, dopants or contaminants in semiconductors. Ion impact energy is adjusted depending on the depth of interest and required depth resolution. Low energy refers to down to 150 electron volt, is used to reduce atomic mixing due to the collision cascade and improve depth resolution down to the sub-nanometer level. High energy, this refers up to 20 kilo electron volt, is selected to investigate deeper. Deeper means tens of microns faster, the sputtering rate of micrometer per minute range, and to improve detection limits. Dynamic SIMS is also frequently used for high resolution imaging analysis and high precision isotope ratio measurements.
Bulk contamination composition studies. In this, the main focus is to establish the presence of impurities or set upper limits to their concentration level in solids. Characteristic feature is to strive for maximum secondary species intensity, that is, high density energetic primary beams. Achievable detection limits are typically in the either parts per million or parts per billion regime, but vary considerably with impurities. That is, these shall vary very significantly with impurities or the level of impurities. Talks about bulk contamination composition studies. An entirely different application is found in the field of geography. Isotopic abundances vary slightly with origin over the Earth's crust, and the isotopical composition of extraterrestrial rock may differ significantly from their encountered ones here. So SIMS may provide a means of locating or assigning a specimen. The mathematical expression that is used for SIMS is explained. It gives the SIMS equation. The equation of SIMS is as follows, which has been given in this slide, and various parameters which are there are secondary ion current of species M, primary ion flux, Ym is the sputter yield, alpha is the ionization probability, theta m is the fractional concentration of M in the surface layer, and eta is the transmission of the analysis system. The SIMS equation has been further elaborated. Ym refers to the total yield of sputtered particles of species M. It could be neutral, the species could be ionic, and what is the per primary ion impact on these particles can be explained by this parameter. It increases linearly with IP. It also increases with energy, but in a linear manner, and maximizes with energies at around 10 kiloelectron volts. Ionization occurs during the emission of the sputtered particles, with the consequence that the sample source participation in the electronic process, which means the secondary ion yield, is strongly influenced by the electronic state of the material being analyzed or used, as I called it, and it is very sensitive to the electronic state of the atom or of the molecule to be ionized and to the source from which they are emitted. It should also be noticed that the secondary ion yield of different species, that is atoms or clusters, sputtered from the same sample source is a function of the ionizing potential of the sputtered atom or cluster, but it can be greatly increased by the presence of electronegative species, that is oxygen, at the surface. Now students, we shall learn about the primary operating condition of SIMS. Ion bombardment of a surface may lead to drastic changes in chemical composition and structure. These changes are like sputtering, amorphization, implantation, diffusion, chemical changes, and so on. All these changes are confined to a very small region surrounding the path of the primary ion into the solid. For static SIMS, each subsequent primary ion hits an undamaged area and a total of only 0.1 to 1% of the atomic sites are bombarded during the measurement. Primary operating conditions have been described. To ensure this, very low primary current densities are used. These have been given here. Primary operating conditions have been given here to ensure very low primary current densities. This results in extremely small sputtering rates of fraction of a monolayer per hour and hence small secondary current density. These reasons make static SIMS a purely surface analysis technique causing negligible damage to the surface and with detection limit as low as 10 raised to the power 8 monolayer, which is extremely low, and this is one needs to appreciate that such low values can be detected.
Next, we come to damage, cross-section and static limit of SIMS. As a result of primary ion bombardment, the sample surface is heavily modified not only by the loss of secondary particles but also by a variety of further radiation effects such as primary ion implantation, mixing of atoms, fragmentation of surface molecules or molecular structures. It is estimated that the impact of a kiloelectron volt primary ions leads to a damage in a region of several nanometer in diameter around its trajectory. This damage can be characterized by a damage cross-section sigma describing the average size of the surface that is modified by a single ion impact. This area strongly depends on the surface composition and on the primary ion properties. Surman and Beningoven obtained damage cross-section of around 10 to the power minus 14 centimeter square for amino acids and other small molecules on metal substrates. Additionally, to retain the molecular information in SIMS, it is essential that no primary ion strike again to an already damaged region. This is achieved by using the static SIMS mode, where an extremely low dose of primary ions is used, such that within the time scale of the experiment, very much less than 1% of the top surface layer constituents receive an ion impact. Under these conditions, on a random impact basis, no spot on the surface contributing to the spectrum should receive more than one primary ion strike.
Well students, from the above discussion, about SIMS, we can conclude some important features. These are: it is a surface analytical technique that make use of an ion beam for sputtering and analyzing the masses of the different ions that are of interest among the sputtered species. When any particle of the lower rash beam size hits the surface, it is ejected out. While being ejected, the sputtered particle can easily get ionized to some extent, or even if it is to a little extent, in the presence of collision. In the process of collision, the sputtered particle is further ionized by the analyzer, and the results are further displayed on the computer screen. The technique has very many advantages, the most important being it's very highly sensitive. It is surface specific, which is not there in many techniques. You get high order of specificity, and very high dynamic range is given by this particular technique. Thank you very much.